Okay, in this segment I want to talk about another way of expressing the signal, okay? But in order to do that I have to explain the refrigeration cycle first. I don't have a chance to talk about that yet. So far what we've done is we have done the heat engine. We have a high temperature reservoir, low temperature reservoir. I put a thermodynamic cycle device over there. This is QH, this is QL, and this is the W net out. And I said W net out from first law will be equal to QH minus QL. As long as I minimize QL, I have higher output from my engine. Okay. Now I'm gonna do the reverse of it. Actually, I will have a TH over here, I will have a TL over here, and I will still have a cycle, a device operating in a cycle. And I'm kind of like doing this now. You see, QL leaving the cold reservoir. Actually, QH is moving into the high temperature reservoir. And you can imagine this. It's hard to do it, so I have to somehow input some energy to it, right? It's not gonna just let it itself, go here to a higher direction, right? It's like if you have a cup of coffee, if you leave it outside, it's gonna cool down. The natural way is to go this way, not that way. So in order to do that, I have to pay for it, right? And if you know, well, you do know that refrigerators, I plug it into the outlet, right? So because I have to supply some power to it, and this is what I'm talking about, input to it, okay? And I will do the same, arrangement. E in minus E out is equal to 0 because it's a cycle, and so basically E in is equal to E out, right? From here, and the in is I'm talking about the system as this refrigeration cycle, okay? And the E in is W net in, and QL is also in, right? Is equal to QH. And if I write this, D net in is equal to QH minus QL. Do you see a resemblance to here? Okay, so this is very similar. It's like the reverse of it. Okay, so what I want to do is I did in the heat engine section too. I want to talk a little bit about this. Okay, this cycle itself in a little bit more detail. Okay, so I want to draw the cycle for you, but just give me 1 second. I'll be right back. Okay, I'm back with the cycle drawn. So let's talk about a couple things over here. So this is where, for instance, this is the refrigerated space. This is inside of your refrigerator. I want it to be low temperature, right? So I'm extracting energy from it so it stays cool, right? And the device that does it is the evaporator. Okay, I'll talk a little bit more in depth. By the way, this is the direction of the cycle. It goes like this, okay? Then I go to the compressor, and I go to the condenser, and condenser dumps heat into the high temperature environment, okay? If there's an air conditioning, for instance, it's the same thing. So instead of this refrigerated space that I have, now this will be my room. I'll remove air from it, or rather heat from it, and I will dump it to the outside, okay? And there's another thing called the heat pump, and heat pump is operating AC in a reverse manner, okay? So what happens is, this is at colder temperature. This will be inside of your room. Outside will be cold, inside will be hot, but I still want to put even more hot into it, right? I want to keep it hot. So what I do is I take this from outside evaporator and I run through this cycle, and I put heat into my room. Okay, so that's the heat pump versus air conditioning system or refrigeration system. Okay, but let's talk a little bit about let's number them. So let's call it 1. Let's call this 2. This is a compressor. That's what you have in the refrigerator, and this is called the expansion valve. I'm not responsible for knowing exactly all the details and design parameters of it. This is in thermodynamics 2, 3, and 4. But I want to talk a little bit just to give you. So this compressor that I go from 1 to 2 is the goal is to increase the pressure. Okay, so I kind of we talked about the compressor in module 5. So the goal is to increase the pressure in here. So I get here, and obviously I have a work in over here. This is where it comes in. Okay, so I have to pay for it. And the vapor, I have a vapor over here. It's compressed, and typically the temperature will rise as well. There's nothing I can do about it. Okay. Then I go through the condenser. Okay, and the condenser is the fluid, we call this refrigerant, by the way. The fluid that passes through the cycle is refrigerant. the refrigerant passes through the condenser when I go from 2 to 3. I don't have any work done on the fluid, but it is cooled because I'm removing heat from it, right? It has to be cooled. It has cooled to the saturated liquid. And I want to inform you that if you look at here in Florida, if you look at outside, you will see the condenser units of your air conditioning systems. That's what I'm talking about. Okay. So I have air. I have around the tubes that containing the refrigerant, and there's a fan that's working, right? So that's what it's doing. It's a condenser. That is this what it is. Okay. And then I go through expansion valve. I talked about this as well. Throttling devices is the general name for it in module 5. I don't have any work input to it or out of it. I don't have much energy transfer, heat transfer to or from the refrigerant. But the goal was to remember that it is to draw the pressure, reduce the pressure, because I increased over here. I want to reduce because it's a cycle, right? The goal is to reduce pressure. And if you remember from module 5, it was a constant enthalpy age process for this expansion valve. And obviously, as I talked about, the temperature drops significantly as well when I drop the pressure. And this evaporator, if you look at, for instance, the air conditioning units, that's what you have in the attic or inside of your home. And you see like more like a triangular shape to it, okay? And you see some basically bunch of different tubes going over here, and I pass air through it, okay? When I pass the air inside of the air through it with cold tubes, what happens is the air gets cooler, and I simply distribute it to the rooms that needs the cold air. And I go through the same process. So now I'm at 1, right? After I go through this evaporator, I'm at 1. Keeps going on and on and on and on. And if I want to do this, it's like this. This is the direction of it. Again, for mechanical engineers, there is much more. We discussed this. We have the Otto cycle for heat engine. We have the steam power plant Rankine cycle. We have the Brighton for the heat engine too. We have a diesel cycle, refrigeration, air conditioning, and heat pump, and other cycles we cover. Okay, but so far this is sufficient for me to, talk about the second law of thermodynamics. But before that, I also want to talk about the thermal efficiency of a refrigeration system, which is AC and refrigerators, as well as the heat pump. Okay, as you remember, this is how we define the efficiency, the output that I intend to have versus how much I need to pay for it. This is my input. Okay, the thing about refrigeration cycle is my efficiency turns out to be sometimes, or rather majority of times, is more than 1. Okay, so that's why we don't use efficiency, because it throws us off. We know when I write it this way that it is from 0 to 1, and this is about 1. So we use something called a coefficient of performance, okay, of a refrigerator. And if I look up here in the cycle that I have, I think this is easier to this way. So the goal for an AC is, this is the room, right? I want to remove heat, so that is the goal. If this is a refrigerator, this is the refrigerated space inside of the refrigerator. So I'm still removing the heat from it. So that is the output. That's what I want. And the input to the system, you can see over here, is this, right? This is the electricity cost, how much it's costing me to run this air conditioning system or refrigerator. So W net in, okay? And I did it up there, so I want to write this W net in terms of QH and QL. It is the same thing for both for the heat engine and refrigeration cycle as well, except this is an in terms of the direction, that's an out, okay? So this is nice. But the only thing that I also want to cover, I need to cover, is the coefficient of performance of the heat pump, because the goal is different. You see, I said the output. Output of a heat pump is, I have a room which is hot and I want to have this QH coming into it. I don't really care about this component, right? This is outside air. This is how much outside air I am extracting from the air and going into my room, which is already hot. So basically QH is what I'm interested in. So it's kind of different, QH. And the input is still the same, right? I have only one input. And you can write this as QH minus QL if you like to as well. And I can make a relationship between those two. You can see this way. If I write COP of HP minus COP of refrigerator, let's look at the right hand side. It's going to be QH by QH minus QL minus QL by QH minus QL. Okay, this becomes QH minus QL divided by QH minus QL obviously this becomes 1, right? So COP of HP will be then 1 plus COP of refrigerator, okay? As you can see from here, the coefficient of performance of a heat pump by definition will be more than 1, okay? And typically actually the coefficient of performance for refrigerator is typically 1 as well, or rather more than 1 as well, okay? So you can see I can reach 2. So think about this. I am getting, for instance, it's consuming 5,000 watts, my heat pump, okay? But the amount of heat that comes to my inside to the room, if you look here, this is what I'm saying is this is 5,000 watts. But inside of my room, if it's 2, then I'm going to have 10,000 coming in. So it's like a magic, okay, per se, from that angle, okay? Okay, now I'm ready to write the second statement related to the second law of thermodynamics, okay? Let me write this down, but actually let me write the title of it, Clausius Statement. Okay, let me write it, I'll be right back. Okay, Mac. So here's what it says. It is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from lower T body to a higher T body. Okay, simply this is what it says. If I draw this, I have this refrigeration cycle, I have TH, I have TL, I have QL, I have, let's say, QH, right? It is saying that this is not going to work unless I have some kind of input to it, okay? So it automatically will not go up. This is the same statement as I leave my cup of coffee, hot cup of coffee, I leave it at the room temperature, it's going to cool down, it's not going to go up. That's what it's saying, okay? So this kind of makes sense to us, right? Also, if you think about the refrigerator, so basically what it's saying is if you unplug it from the wall, it's not going to work. That's it, what it says, okay? I told you about the refrigeration cycle, that's why I covered it, okay? So if you just unplug it, it's going to get warmer and warmer inside of the fridge. Makes a lot of sense. When the AC or the electricity goes out, the inside of the refrigerated space goes up too, okay? Okay, now I have two statements. One is the Kelvin-Planck statement, one is Clasius statement. And you may think these are for two different things, and it is. One is for heat pump, or rather the one is for the heat engine, the second one is for the refrigeration cycle. But I want to show you something saying that they are actually the same, one and only, okay? Let's say that this is my cycle, refrigeration cycle, and let's again say that this is QL. Let's say that there's no work input, okay, which is not good according to Clausius statement. I had to plug this into an outlet, right? But let's pretend that is the case. And if I do an energy balance over here, if there's no inlet, there's no exit, this needs to be QL2. Whatever comes in must come out because this is a cycle at the end of the day, right? So this will be QL2 from first law, okay? Let's operate another device, a heat engine, from a same difference temperature reservoirs, okay? It's going to be QH, it's going to be QL, and I'm saying that this works as if it should work. Net out, and if you remember from the first law, we said that this is QH minus QL, right? Okay, so what is wrong with the system? What is wrong with the system is it is violating the Clasius statement. That is what it violates. Why? This part is fine, there's nothing wrong with this part, but this part is a problem, okay? So now what I want to do is I want to kind of switch gears a little bit and look at this whole thing as a system, like a combination of those two, and see what happens, okay? So I want to go ahead and redraw this. So I have a TH over here, I have a TL over here, and I'm simply drawing this dotted line. That's red, but pretend it is green for now, okay? So let's look at this high temperature reservoir, what's happening. I look here, so QL is coming in to the high temperature reservoir, but the QH is leaving. So if I draw the energy transfer between this dotted cycle and the TH, and if the arrow is that way, this is going to be QH minus QL. Okay, so that's fine. Let's do the same arrangement for the low temperature reservoir, and you can see QH is leaving the low temperature reservoir, QL is coming in to the low temperature reservoir, so the net effect is I don't have anything in this, they cancel each other, okay? And let's look at the work out from this system, and you will be seeing that this is going to be QH minus QL, and which will be equal to W net out. Okay, some of you may have already seen it. Do you see what this one violates? This is the exact statement of Kelvin and Planck statement. Okay, it is violating the same device that violates the Clasius statement, also violates the Kelvin-Planck statement. So these two statements are the same, or rather the main message that it is conveying to you is the same. Okay, all right, so that's gonna do it for me. I'll be back with an example for refrigeration cycle. Thank you.